Start chapter 2, which refers to atoms, ions, and elements. Does everyone know the meaning of what an atom is, what an ion is, and what an element is? We went with it, we used the terms last week. And if you take a piece of graphite, like your graphite from your pencil, and you cut that and cut that and cut that, and you speed it, you'll still end up with graphite, because you're just cutting it. So the word atom comes from the Greek word atomos, meaning indivisible. We cannot divide a carbon atom, and here is carbon in our periodic chart, right? We will be covering how Russian scientist Mendeleev came up with a periodic table. And it's very important for us to know that atoms are composed of ordinary matter. So matter is made up of atoms. And one way of understanding the behavior of atoms is through the scanning tunneling microscope. And before we go further, I'd like to share with you a video on IBM Zurich, quite a few years back, came up with the idea of a scanning tunneling microscope. And let's see how they came up with it.
The scanning tunneling microscope has about a 35-year history, and IBM has been very much involved in every step of this way. So it started with two famous guys, Gerd Binnig and Heini Rohrer, who are IBM scientists. They were scientists in our Switzerland research facility in Zurich, and they had the crazy idea that you could actually hold a metal needle close to a surface and use it for imaging. And so they both received Nobel Prize in Physics in 1986 for this. Then this particular laboratory here at IBM Almaden was the first to be able to move atoms. So Gerd and Heini used it to see the atoms, and then Don Eigler here at IBM Almaden used it as his hands and position atoms and write the famous IBM logo that many of you have seen. And so we also have a long history locally here in using this tool to build structures and look at these structures. My contribution in that list, is a much smaller one, of course, but my contribution is to be able to look at magnetic properties of atoms on surfaces. So, I build on the big developments that other guys have made, and add to that the magnetic imaging, which has been very successful for the last 10 years.
So that's so cool, huh? So Binnig and Rohrer developed a type of microscope that could see atoms. And like he said, you can actually get an individual atom, and you see how they made IBM one at a time using the scanning tunneling microscope. So this is actually how we can image and move atoms around. So the atom is the smallest identifiable unit of an element. There are 91 different elements and over 20 synthetic ones. But some early building blocks of matter. Democritus wrote that matter was composed of really small indestructible atoms. Nothing exists except atoms and empty space. Everything else is opinion. So later on, this was established, and an English chemist, Dalton, provided the evidence behind it and came up with modern atomic theory and some laws that state matter is composed of atoms. And from here we came up with the law of conservation of mass, where matter can neither be created nor destroyed, right? Likewise, they came up with a law of definite proportions. So we'll look at the law of conservation of mass, it was Antoine Lavoisier who formulated this, that in a chemical reaction, matter is neither created nor destroyed, only transformed. So if you look at sodium metal, and in the lab, one of the last lab exercises would be you would take a piece of sodium metal and see how it reacts with respect to water, and it'll be jumping around, and you see a vigorous reaction when it is placed in water. But when you combine sodium with chlorine gas, you get a very harmless stable salt. So matter can neither be created nor destroyed, only transformed. And then we come up with a law of definite proportions, where samples are given that always come up with the same proportions of their constituent elements. So in other words, if you want to decompose water into hydrogen and oxygen, have you ever done that in, tried to split water? Next time I'll bring a couple of pencils and connect it with a battery, and then hook it up. And you'll see, what do you think when we put it in water? Bubbles will arise on both pencils, right? And where it bubbles more is where oxygen gas is being evolved, and where it bubbles less, because there's two hydrogen and one oxygen. So we'll try to demonstrate that reaction next week. I'll bring a couple of batteries and a couple of lead pencils. So you always come up with an oxygen to hydrogen mass ratio of 16 grams of oxygen with 2 grams of hydrogen, or 8:1. So that is what's referred to as a law of definite proportions. It always combines or decomposes specifically in a definite way. So Dalton came up with a law of multiple proportions, where in fact, if there are two elements A and B that form two different compounds, the mass of element B will combine with A in a particular ratio. So for example, you have carbon dioxide or carbon monoxide, right? And so if we look at carbon dioxide, we saw this last week, the mass of oxygen that combines with 1 gram of carbon is 2.67 grams. For carbon monoxide, it is 1.33, and that ratio is 2.67 over 1.33 is always a whole number, which is 2. So Dalton came up with a theory then that says each element is composed of tiny indestructible particles called atoms. And number 2, then all atoms of a given element will have the same mass. And these atoms combine in simple whole number ratios, so that in a chemical reaction, atoms only change in the way they are bound together. You know, the bonds that join them together. Then we want to go a little bit into the background on how the electron was discovered. It was J.J. Thomson who came up with the cathode ray experiment. The electron, he found out, carries a negative charge, and he measured this value. It came up consistently to be minus 1.76 times 10 to the third coulombs per gram. And then another scientist, Millikan, he came up with the charge of the electron to be minus 1.96 times 10 to the minus 19. And later, an English scientist, Rutherford, came up with the plum pudding model of the atom, and it looks like this. The plum pudding, right? For those that have probably English lineage, during the holidays you have plum pudding for, as part of your holiday meal. So then that wasn't quite right either. So later on, they came up with a nuclear theory of the atom, and it was Rutherford that proposed this, that in fact most of the volume of the atom is empty space, and that negatively charged particles are dispersed around. So in other words, we no longer have this model where we have a big nucleus with electrons like stuck in like plums or raisins, but in fact we have protons and neutrons inside the nucleus, and the electrons are orbiting around at very discrete energy levels. Then later on, they also found that there are in fact also neutrons inside the atom. So if you picture the atom with protons, so I'll put P plus. And then electrons. Actually, the electrons won't be there yet. First, neutrons, which are neutral. And then somewhere around here are electrons. Electrons may be going that way and just orbiting the atom. But not like our solar system. No, we will learn a little bit later how the electrons are arranged in a couple more. Chapter 3. So our subatomic particles are protons, neutrons and electrons. So the proton and the neutron are inside the nucleus, right? So they are inside the nucleus, while the electrons are outside. So the charge of the proton and electron are equal in magnitude, therefore an element has no charge. And elements are defined by their number of protons. So if we look at an element, say, if we look at lithium, Li, they are defined by their number of protons. So lithium there, it says 3, right? On the other periodic table. So there are 3 protons, then therefore it has 3 electrons, and therefore it also has 3 neutrons. Got it?
No.
No?
It may have 3.
No.
May have, yes, yeah, not yet. But for now, we'll just assume that it does, right? We have to go to the word isotope a little bit later. But when we say carbon 12, you see carbon, here's carbon here, right? And you see carbon over there, so carbon 12. And there's also carbon 13, right? So carbon 12 has 12 protons, 12 electrons, 12 neutrons.
Where's carbon 12 in the periodic table?
Carbon is number 12. Carbon,
Number 6.
no, we call it 6, sorry, my bad. When I say carbon 12, because when we talk about isotopes and imaging, we refer to carbon 12 and then carbon 13, right? So carbon is here with 6 protons.
Right, I see it there. Okay.
And then over there is also carbon 6, yeah. You see that?
How they get those numbers?
Yeah, good question. How did they know that there are in fact 6 protons and 6 electrons? So it didn't start out with carbon. It started out, I think, with either iron, some metals. We'll see this a little bit later when Mendeleev, the Russian scientist, as he was taking the train to and from his work in Russia, right, he was playing solitaire, and he noticed that, I think those elements that I've been working recently, they seem to have the same properties. So I said, gosh, sodium, potassium, they seem to have the same properties. And calcium and magnesium, they seem to have the same properties. Why don't I put them on that side and call them the metals? And chlorine, bromine, they seem to have similar properties. And so he started putting them in certain, in certain columns, and then also in certain rows. And that's how the periodic table came about. But I'll show you how that was developed. But first they had to figure out what the atom was composed of. And hence you had the gold foil experiment, Rutherford's gold foil experiment. And before that was the experiment first performed by J.J. Thomson on the cathode ray tube, right? So he would notice that when he would bombard his cathode ray tubes, something was always being deflected. And it turns out it was the electrons. So as we go on, right, so the elements are defined by their number of protons. So carbon has 6 protons, nitrogen has 7 protons, oxygen has 8 protons. Is that right? Okay. And if you look at our periodic table here, the way it's arranged in our slide, Be for beryllium is the number 4. As an atomic number of 4, that means there are 4 protons. Right? So the atomic number corresponds to the number of protons. You have the chemical symbol and the name. And then as we go on to the next slide, they may have different neutrons. And this is where carbon may have 6 neutrons, 6 protons, 6 electrons. But then there's another carbon, so we call that carbon 12, right? Because when you add, because the atomic mass, which we'll define shortly, where's carbon here? We say it's carbon 12, but then there's also carbon 13 because there are 13, we say it's carbon 13 because instead of just 6 neutrons, there are 7 neutrons. So our PowerPoint slide talks about neon. So neon is 10, right? You see 10 on the top right on neon? Does everyone see that?
Right, all the way on the...
Yes, the far right. Huh? But then it could actually really have not just 10 neutrons, it could have 11, it could also have 12. And we refer to the different number of neutrons as isotopes. Okay, so make sure you know that isotopes are the different number of neutrons. So when we write down the sum of the neutrons and protons of the atom, and you will note that in this chapter's quiz, it was actually asking how do you find the mass number in multiple choice. So you want to bubble the one that the sum of the number of neutrons and protons give you the mass number. And the mass number is the one, I would say carbon 12 because carbon 6 protons, 6 neutrons, right? So carbon 12 with carbon 13 would be 6 protons, 7 neutrons. Any questions? And there's also, I think chlorine also exists as chlorine 35 and chlorine 37. So in other words, chlorine 37 has 2 more neutrons than chlorine 35. So let's go to the other big topic. What is an ion? So when you have a sodium, I'll just pick up sodium here. When we have sodium, what does sodium, what does it tell us? That sodium has 11 electrons, right?
11 electrons or 11
Or
protons?
11 protons. But because it's neutral, it also has 11 electrons, right?
Oh, okay.
Yeah.
How do you know it's neutral, miss? Just curious.
How do we know? We first we'll assume.
Okay.
Okay? So we'll assume they're the same. So any 11 should have 11 protons and 11 electrons. How many neutrons? 11 also. And then what? And so if we want to remove an electron from sodium 11, so sodium 11, when we write the element in its natural state, we'll put a 0 because it has no charge, right?
Right.
But when we remove an electron, what happens to it?
It has a positive charge.
Yeah, so it will become Na plus E minus, right? So what happens to the number of electrons? How many electrons now are in sodium plus?
10.
So then it will just have 10 electrons, while here there were 11 electrons, right? Yeah,
Wouldn't the neutrons be 12 since the mass is 23?
20, yeah, it's 20, yeah, but it's really 11. Yeah, because we will,
So you can round up to 23 and subtract 11 to get 12.
yeah, but it's not, because the atomic mass itself is a ratio of all the isotopes, so it's not a whole number. Okay, so like for example, I can make, because I remember this clearly, when we look at chlorine here, chlorine is 35.45, because chlorine has two isotopes, chlorine 35 and chlorine 37. And so the mass number is an average, they're averaging based on the percent that it's found in nature. So one has 75% more. So this one exists 75% more than this, hence the number there is, who can read the actual atomic mass of chlorine?
35.
5,
45, 27.
4, 5,
45, 27.
thank you. 4, 5, 2, 7.
So you don't want us to ever round that number then?
No, when you do calculations and so forth, you'll probably be given either like so, right? Or you'll probably be given an atomic mass with the 4 significant figures. Okay, so that's when we say when you lose, right? But what happens when you gain? So let's so we know that chlorine tends to lose the electron, while sodium tends to lose the electron, while chlorine tends to gain that electron, right? So if we have chlorine and we want it to gain the electron that sodium lost, what happens to the charge here? How will we write chlorine? It will be Cl minus, right? So from here, if we say if there are 35 electrons, how many electrons will be here? 36, right? So if there were 35 electrons, then this would gain an electron, so 36 electrons. So ions can lose or gain, and so sodium plus, or the example used there is the fluorine, or we call fluoride. Once they lose an electron, we don't call it fluorine anymore, or chlorine, or gain the electron, we call it fluoride or chloride. But we still call it sodium when it loses an electron, or potassium or calcium. So when they are in group 1, they tend to lose 1 electron. When they're in the second column, like magnesium, Mg, and Ca, they tend to lose 2 electrons. And we'll find out why, because based on the number of electrons on the outside shell. Okay? So, therefore, Mendeleev organized a table that put the ions, say lithium, sodium, potassium, because they all had the same similar properties, similar chemical properties, similar chemical properties, chemical and physical properties. And so he arranged also the rows of elements that were in the vertical column, and he arranged them in order of increasing mass so that the properties would recur periodically. And so here's a more modern periodic table. So we refer to this as group 1A metal, group 2, and when we look at the 7A here, we call this the halogens. And all of these elements, they actually all want to be in a happy state, like all the elements that are listed in the right-hand column, where you have helium, neon, argon, krypton, and those we refer to as the noble gases. So when you combine sodium plus and chloride minus, they form sodium chloride, and they are in a heavier, lower stable state, non-reactive. So once again, metals lie on the lower left side of the middle periodic table and share properties like conductors of heat. So here are our metals, right? Sodium, potassium, rubidium, cesium. They are, you can pound them. Have you tried to pound metal, right? You can do that with aluminum. You can pull them into wires, and they are often shiny. So they tend to lose electrons. So metals, you want to write down, lose electrons when they undergo chemical changes. And nonmetals, on the upper right-hand side, so when you look at the upper right-hand side, the nonmetals, oxygen, right? Nitrogen, nonmetals, carbon, fluorine, so these are the gases, neon. These are the halogens, and so you have oxygen and so forth. So nonmetals on the upper right side of the periodic table. 5 are solids at room temperature, like C for carbon, P for phosphorus, S for sulfur, Se for selenium, and I for iodine. Only one is a liquid at room temperature, that is bromine. The gases, 11 are gases at room temperature. So nonmetals on the upper right-hand side. So therefore, they do not conduct electricity. You cannot pound and make them ductile and malleable. You can draw them into a fine wire, and they tend to gain electrons when they undergo chemical changes. So then in the middle, and if you have your textbook, which is really cool, let's take a look at your brand new book. You will notice that the periodic table here shows a jagged line, and also these purple ones here are referred to as the metalloids, because they have properties of both metals and non-metals, right? So metalloids of silicon, a semiconductor. So several metalloids can be classified as semiconductors because of their intermediate electrical conductivity at very high temperatures. So here's that, so silicon, germanium have been made into chips for IC or circuits, or integrated circuits. So noble gases, once again, may be referred to as the group 8A or the column 18 in our periodic table. They are very, very unreactive, so noble gas, right? Very, very stable. Helium, very stable. We use neon in electronic science. And then we refer to the group 1A as alkali metals, and the group 2A as alkaline earth metals. So alkali, alkaline earth. And of course, group 7A are the halogens. And here's iodine and chlorine, and bromine is a brown gas, but reddish brown that easily evaporates into a gas. So it's a liquid that evaporates into a gas. So to summarize, group 1A tends to lose an electron, so forms a 1+ cation. Group 2A forms a 2+ cation. Halogens tend to gain 1 electron, so they are referred to as fluoride, chloride, bromide, iodine, and ions. So when you have a positive, so a sodium, so chloride, we would call this chloride, Cl minus. A negative one is an anion. And then a positive one would be, we call it a sodium cation. You see the difference between the two, right? One's a cation, so it's easy to remember cation because it's got a plus, and anion would be the negative charge. So any questions so far as being able to distinguish between an atom and ion? We can right now, right?
No.
So, no, not yet. Ions in the periodic table, so we could have H+, Li+, Na+, K+, or on the far end here, we could have F-, Cl-. We could have nitrogen 3-, oxygen 2-, and it's hard to quite understand that why, right? Because we have to talk about how the electrons are, and that's chapter 7 of our text. We will be covering it shortly. So naturally occurring chlorine, so chlorine 35 consists with a mass of 34.97, has 75, almost 76%, while the other one. So then we can calculate and convert what's the percent abundance. And this will explain why chlorine has an atomic mass of 35.45. So you will note the atomic masses themselves are not whole numbers, but will have, sodium is 22.9 something, right? So when we look at the atomic mass, so the smaller number is is referred to as the atomic number, and the larger number is referred to as the atomic mass. So the atomic mass is really the sum of the fraction of isotopes in each element. So how do we measure the mass of the atoms? We use a mass spectrometer. And when you take organic chemistry, this is one of the equipments that we use to determine the different masses. And how does this work? Well, we have an electron beam that will ionize a sample as we put it through, vaporize it, and in between the magnets, and it separates and breaks down the masses. So for the chloride 37, we get, when we plot the percent, the intensity of it, we get a heck of a lot more of Cl35 and only about a small fraction of the chlorine 37. So we need to go to the next important topic of the evening. What is a mole? Not the mole, the biomole, right? But the mole is referred to as the chemist's dozen. So 1 mole of carbon weighs, so the atomic mass of carbon is how many grams? 12 point, right? What does it read here? Yeah, right? And then 1 mole. So in other words, we would say, to make it clear, or 1 mole of anything is 6.022 times 10 to the 23rd units of that thing. So in other words, we could say, we'll take, think of an element. Give me an element and a symbol. And a symbol. So 1 mole of sodium atoms, right? 1 mole of sodium has 6.023 times 10 to the 23rd atoms. But 1 mole of sodium weighs 22.9 grams, right? Okay, weighs but 1 mole of, I'll put here 1 mole of hydrogen also has how many atoms? Also 6.023 times 10 to the 23rd atoms. And how many grams does it weigh? And weighs what? 1.008 grams, right? So we'll say 1 gram. Is it 1.008 grams? And then what else? Find another one for me. What would be another good example? What's Fe? Iron, right? 1 mole of iron, Fe, has 6.023 times 10 to the 23rd atoms. And weighs, how much does Fe weigh? 55.845, okay. 845 grams, right? That's what this means when it says 1 mole of anything is 6.022 times 10 to the 23rd. We gotta make this 2. Sorry. I saw the 1 mole of anything, right, is 6.02 times 10 to the 23rd of that thing. So that's what that means. And this is a very, very important concept to remember as far as chapter 2 is concerned, right? Okay. Because we will need to be able to convert grams into atoms, atoms into moles, and vice versa. So converting between mass and moles, so we already know that aluminum is 26.98 grams, and 1 mole of that has 6.022 times 10 to the 23rd atoms, right? Likewise, carbon. So you'll note, and you can find a pattern that the lighter the atom, the less mass is in that 1 mole. It still has the same number of atoms, but the mass now is less because it's much lighter. And so when we try to convert the number of atoms of an element by weighing it, first we obtain the mass, then we convert it to the moles, and then we convert the number of atoms using Avogadro's number. So let's go back to our the content on chapter 2 on D2L. You will note that the PowerPoints are there, and there's a concept chapter 2 that you can print out just like chapter 1. And there's also a quiz on chapter 2 that you can take. Oh, I may not have, yeah, there are 10 questions, and the first question has to do about, I think this has to do with the conservation of mass, so you may want to know what were the 3 laws, right? The law of conservation of mass, definite proportions, and what are the different types of subparticles, how to recognize an element, what's an isotope, what's an ion, what would be a charge of an aluminum ion. So if we look at aluminum, right? So aluminum would be positive because it is yeah, some of you are way ahead of the game. Aluminum tends to lose 3 electrons, and it's in a group 3. So it tends to lose 3 electrons, and so it would have 3 plus. Oxygen tends to gain 2 electrons, so it would have 2 minus. So we still call this an aluminum cation, but we call this an oxide anion.
So when is that quiz due?
Mhm.
Chapter 2.
Yeah.
I mean, not chapter, yeah, chapter 2, when is that quiz due?
Oh, this one?
Yeah.
It's actually something that helps you. You want to do
Okay.
it before ultimately what actually is nice is to look at it and take it the first time without having do it like a pre-quiz, without having went through the lecture, and then after the lecture, then take it again, and you will get probably all of them right. Yes, so twice. So it's another tool to get, the different concepts and topics in a test-like format. And I did the same thing for chapter 1 also. So you click on the matter and measurements in chapter 1, and you also have similar similar type of format where there's a density problem, there's a significant figure calculation, there's a volume probably determination, right? Or definition, because here's one is calculate the volume. That's a physical property, so it's a physical property, then therefore you need to know physical changes, chemical changes, what's the difference with minerals, right? Okay, so it gives you, different ways of really understanding the subject matter, because these days, memorization just takes us, so far, right? And so I want to spend the rest of the time to do actually problem solving as far as problems in chapter 1 and also problems in chapter 2. So I will try to access my Master in Chemistry online.
Do you have assignments on mastering chemistry?
Yes, I actually, if you like to use it, I can give you a course ID number. Who was that asked me?
I like.
Yeah?
I'm fine.
So, yeah, I've been using Master in Chemistry actually since 2003, ever since I taught at Mandy.
That's kind of like the same concept as my math lab and stuff like that.
Yeah, there's also, exactly,
Okay.
it's very, very similar. It costs some, and some at Dade, they wanted us to, use this so that the students.
Like once you put it on your computer, you'll be able to
Yeah.
see.
Really?
Yeah.
You're around 7
Oh,
minutes.
can you take it off and I'll put it in here?